Hello everyone, I'm Praveena from Group 320. I'm going to explain about the modeling of dynamic biological process. In this one, my topic is lotka-volterra models. Modeling of dynamic biological process. The lotka-volterra models. In lotka-volterra models are mathematical models. It is used to describe the dynamics of biological or chemical systems. Involves interactions between the two or more species, such as predators, prey relationships, or autocatalytic chemical relations. These models are examples of non-linear systems, which means their behavior is not proportional and can involve the feedback loops and oscillations. The origin of models. If we talk about the origin of models, about Lotka it is in 1920. It focused on chemical reactions, particularly autocatalytic reactions, where a predator of the reaction catalyzes its own production. In Volterra 1930, it developed the population predator-prey model, which it describes interaction between the predator and like examples of foxes and their prey rabbits. If you see this equation, it tells about the prey population and it tells about the predator population, and these constants describes the birth, deaths, and interaction rates. In Lotka-Volterra models, it helps us understand the non-linear interaction in system, is showing the how populations or concentrations oscillate due to the feedback loops by simplifying the complex systems. Instability conditions assumes the form. You can see this in equation. Stability condition, it assumes the formation, and the only steady state solution corresponds to the condition that we have this equation. The number of prey is X and the number of predators is Y. The behavior of the population in time describes by this equation. And then let us find the steady state values of the variables from this equation. The quantities and x, y are represented in form of this equation. And if we multiply the first equation by this one and second the equation by this one, then add them up, and we can get this equation, or we can get this one. Both of them will get this one, and that is we can get this constant equation. The multiplying the both sides of equation by kk, we have, like, since we have before we got like k1 and all, this equation k2, and then we will get this equation. After dividing by the k1 k2, we find another equation, like another constant equation, and linearizing we obtain this one. Condition for the compatibility of these equations, the characteristic equation, we got this one, and then the imaginary equation, the oscillation frequency is given by this one. The dynamics of the lines and have populations in Canada for the period 1845-1935, according to the data of the fur company. Such a behavior also arises from the spectacular consideration. The larynx population used, but no one was reduced. Like the larynx population increased, but the number of hairs was reduced. We have examined the behavior of a conservative system In fact, the population of species may increases only up to certain point to the values like this one, and corresponds to situations. The maximum of prey production is expressed by the following relations: the Wellhurst equation. And then we have, before we got this equation, the Lotka autocatalysis equations, which are similar to the Volterra equations, also led to a periodic behavior. We see that non-linear asymmetric systems are capable of a time-ordered behavior. We have already seen that ion chemical process in this equation. Then now near the steady state, we can see this equation expands this one, and in a series, like we obtained another equation like this, and then where these derivatives are taken for the steady state. Like generally speaking, it may contain both symmetric and asymmetric parts. If the antisymmetric parts of this one are different from zero, then in the general case, no kinetic potential axis. Suppose that two chemical processes are described by the antisymmetric metric in this one, or then this equation will get such a system relates around the steady state, where getting into it the phase pattern has the form. Then corresponding to the steady state, in the center, introducing the polar coordinators like this in the, and we obtain this equation. But the function of this equation is not a potential. It increases by this equation, and with every revolution. It is exactly this situation that has been that deal with the considering the lotka-volterra systems. Thank you everyone. My explanation is done here. I hope you all enjoyed this explanation. Thank you.